Hello and welcome to 2.6 Related Rates. So, related rates, I guess the best way to describe this is word problems. Yeah, we're going to do word problems with calculus, which is not a big deal. We can handle the word problems. We can handle the stuff. We are capable of doing these things. I know that people get very intimidated with word problems. Like, oh my gosh, how do I translate that? Well, we're going to go through that now. We're going to pick up those skills now and develop those skills for translating from words into math. From English to math. That's what we're after. Okay, we have used the chain rule to find, and they should say, dy dx implicitly. We can also use the chain rule to find the rates of change of two or more related variables that are changing with respect to time. That is called related rates. So suppose x and y are both differentiable functions of t and are related to the equation y equals x cubed minus 2. Find dy dx when x is 1, given that dx dt is 2 and when x is 1. So I want to point out x and y are both functions of t, so when we do our implicit differentiation, we're doing our dx dt basically. So we have y equals x cubed minus 2. We're going to do the derivative with respect to t of y equals the derivative with respect to t of our x cubed minus 2. This will become dy dt, so the change of y with respect to time, equals the derivative with respect to t of x cubed would be 3x squared dx dt, because x is a function of t, and the derivative with respect to t of 2 is a 0. So now we're going to substitute the known quantities. And what do we know? We know x is 1, dx dt is 2, so our dy dt, and I think this should say dy dt, it's going to be 3 times our x is 1, so 1 squared, times our dx dt is 2, that's going to be 6. So our dy dt is 6. Okay, I'm going to go on to the next one. A pebble is dropped into a calm pond, causing ripples in the form of concentric circles. The radius r of the outer ripple is increasing at a constant rate of 2 feet per second. When the radius is 5 feet, at what rate is the total area of the disturbed water? So drop in the pond, you get a circle, and think of these little waves just going out like that. So what is the area of a circle? Go ahead and say it. Okay, good job. I heard you there. It's pi r squared. Very good. So we want the rate that the area is changing. So we want dA dt. So dA dt. So we're going to take the derivative with respect to t of A equals the derivative with respect to t of pi r squared. So our dA dt is going to be pi times 2r dr dt, since the radius growing is a function of time. And they tell us it's going at 2 feet per second. That's the radius increasing. So our dA dt is 2 pi r dr dt. By the way, 2 pi r, what's that? That is the, you're right, that is the circumference of a circle. Yeah, interesting. So our dA dt is 2 pi times, so the radius is what? Well, the radius is 5 feet. 2 pi times 5 times our dr dt is 2. It's a constant there. So dA dt is 20 pi square feet per second. That's how the area is changing. Okay, I'm going to go on to the next page here. Guidelines for solving related rate problems. Identify all the given quantities and quantities to be determined. And they should say make a sketch, if it helps, and label the quantities. Write an equation involving the variables whose rates of change either are given or are to be determined. Use a chain rule and implicitly differentiate both sides of the equation with respect to time t. And after completing step 3, substitute into the resulting equation all the known variables and the rates of change, and solve. A verbal statement: the velocity of a car traveling 2 hours is 60 miles per hour. Math model: x equals distance traveled, dx dt is 60, that's change in position with respect to time, equals 60 when t is 2. Water is being pumped into a swimming pool at a rate of cubic meters per hour, so V is volume. The change of volume with respect to time would be some kind of meters cubed per hour. A gear is revolving at a rate of 20 revolutions per minute. 1 revolution is 2 pi radians. So theta is the angle of revolutions. D theta dt would be 20 times 2 pi radians per minute. So 2 pi because that's one circle, 20 because it's going around 20 times in a minute. Example 3. A point is moving along the graph y equals x squared plus 1. That is a parabola. Such that dx dt equals 2 centimeters per second. Find dy dt for x equals -1, x equals 0, and x equals 1. So we're doing the derivative with respect to t of y equals the derivative with respect to t of x squared plus the derivative with respect to t of 1. So dy dt is 2x dx dt, and that derivative is just 0. Now we know dx dt equals 2 centimeters per second. So dy dt would be equal to, first we have x equals -1. That's going to be 2 times -1 times 2. It's -4 centimeters per second. For x equals 0, dy dt would be 2 times 0 times 2, which becomes 0 centimeters per second. And for x equals 1, dy dt would be 2 times 1 times 2, which equals 4 centimeters per second. Okay, that'll do it for example 3. Go on to another one that says example 3. Am I numbering it wrong? Is that example 2? No, a 2 on the first page. So this next page we're going to go to is going to be, should say example 4, but there's typo. Okay, here it says the included angle of two sides of a constant equal length S of an isosceles triangle is theta. So here's the view in one direction, here's our theta, here's the other one, and there's the triangle. So two sides are of equal length. Now I'll show that the area of the triangle is given by A equals 1/2 S squared sine theta. if theta were increasing at a rate of 1/2 radians per minute, find the rate of change of the area. So we'll be using this formula after we derive it. And theta is pi over 6, and theta is pi over 3. And explain why the rate of change of the area of the triangle is not constant, even though d theta dt is constant. So, in this figure, I mean, if you were to look at this, where here's S and this is H and this is theta, the area is, of course, 1/2 base times height. Now, what would be the calculation for this height? The height would be, what's our relationship between these? Sine of theta is h over s, so h equals sine theta times s. So area would be, of this triangle, this one here, I just use this to help find the height. For s, or for area, is going to be base is s, the height is h, so it's 1/2 s times h, which is 1/2 of s times, what was h again? H is sine theta s, so s sine theta. So area would be 1/2 s squared sine theta. So that answers the first part, for part A. Now for part B, our d theta dt, we're told, is 1/2 radians per minute. And we're looking at theta being pi over 6 and theta being pi over 3. We know our area is 1/2 s squared sine theta. So our derivative with respect to time of A is the d dt of 1/2 s squared sine theta. And in this, s is a constant. So our dA dt is going to be 1/2 s squared times, the derivative of sine is cosine theta d theta dt. So when theta is pi over 6, dA dt, the change of area with respect to time, is going to be 1/2 s squared times cosine of pi over 6 times 1/2 radians per minute. And that comes out to be (1/2 s squared times 1/2 times 1/2). Oh wait, got another one, square root of 3 over 2. That's our cosine pi over 6. And this is square units per minute. And that's really going to be s squared, square root of 3 over 8 units squared per minute. For theta being pi over 3, our dA dt is 1/2 s squared cosine of pi over 3 times 1/2 radians per minute. That's our d theta dt. It's 1/2 s squared times 1/2 times 1/2 units squared per minute. This comes out to be s squared over 8 units squared per minute. So part C says the change area was greater earlier than it is now. And that's because you get it getting bigger, bigger, bigger. And after a certain point, it's going to start getting smaller. So if you think about that area, well, it's not going to keep getting bigger. When it gets smaller, like the bigger this angle got, the closer to pi, or 180 degrees, your area is going to become nothing. So our dA dt is going to be 1/2 s squared cosine theta d theta dt. Now in that, 1/2 s squared and d theta dt are constants. These are constants. But cosine theta is variable. Depends on theta. So this part will vary, where the other ones always stay the same. And from 0 to pi over 2, it's getting smaller, getting closer to 0. So from 0 to pi over 2, cosine of pi over 2 is nothing, is 0. So our d theta, dA dt is proportional to cosine of theta. And cosine theta is not constant. Okay, that'll do it for this example, which we should have said example 4, it says example 3. Okay, we're going to go on to the next one, which says example 4, but it's really example 5. Okay, a ladder, I should have said 25 feet long, not 35, we'll change that. I should say 25 feet long, is leaning against the wall of a house. The base of the ladder is pulled away from the house at a rate of 2 feet per second. This 2 feet per second is our dx dt. How fast is the tip moving down the wall? So imagine here's the house, here's the ladder. So this is 25 feet long. It's going that way, that's our dx dt. And that's going to be equal to 2 feet per second. And then we'll have our dy dt. It's going to be questionable. So how fast is that tip moving down? That's our dy dt down the wall when the base of the ladder is 7 feet, 15 feet, and 24 feet from the wall. So we'll call this our x distance here. Call this y. And consider the triangle formed by the side of the house, the ladder, and the ground. Find the rate at which the area of the triangle is changing when the base of the ladder is 7 feet from the wall. So we have the 3 cases. When it's 7 feet, this is 25. Using the Pythagorean theorem, our height, or should I even say y, is going to be the square root of 25 squared minus x squared. That's 625 minus x squared. So it's 625 minus 49. And what is 625 minus 49? $576, and the square root of 576 I believe is 24, so this is 24 here. And then whenever it's going to be 15 feet away here, and this is 25, our y is going to be equal to the square root of 625 minus 15 squared. That's 625 minus 225. Square is 400, which is 20. This is 20. And in the third case, we have it where this is 24 here. We already know this is going to be 7 from earlier calculations. Pythagorean triples. So, do you want to go with h or y? I did h in my notes, so maybe I'll go with h for the height instead of y, just to be consistent. dh dt. So, based off what we saw here, h would be equal to 625 minus x squared to the 1/2 power. So our derivative with respect to time of h would be d dt of 625 minus x squared, the 1/2. And so our dh dt is going to be 1/2 times 625 minus x squared to the negative 1/2 times negative 2x, the derivative of what's inside, dx dt. So our dh dt is going to be negative x over the square root of 625 minus x squared dx dt. There we go. Now we can get our three cases. And we know that dx dt is 2. So in our first case, x equals 7. So our dh dt, the height, is changing at a rate of negative 7 over the square root of 625 minus 7 squared times 2. This is negative 14 over the square root of 576, which is negative 14 over 24, which is negative 7 over 12 feet per second. In the second case, x equals 15, and again dx dt is still 2, so our dh dt is going to change, you think? You think we're going to have an increased or decreased rate of fall for the top of the ladder as it gets further away? Let's find out. We have negative 7 over the square root of 625 minus 15 squared times 2. That's going to be negative 14 over the square root of 400. That is negative 14 over 20, so negative 7 over 10 feet per second. And then for c, x equals 24, dx dt equals 2. dh dt is going to be negative 7 over the square root of 625 minus 24 squared times 2. That's going to be negative 14 over the square root of 49. So that's going to be negative 14 over 7. And that's going to be negative 2 feet per second. So as we see, oh, there's a mistake here. Yes, there's a mistake. This should not have been that. It was 15 here. And that would have been negative 3/2. Sorry about that. And this should have been negative 24. So it would have been negative 48. Okay. And that's all. Negative 48 over 7. So it really speeds up going down the further this gets away, even though you're pulling down at a constant speed. That going down that side of the house is really speeding up. So I'm going to erase this in just a moment, so pause if you need a pause, so I can do the second part, part B, when we do the area. Now, this last part, part B of this problem, we know the area is 1/2 of base times height. So area is going to be 1/2 of x times the square root of 625 times, or no, minus x squared. X, square root of 625 minus x squared, found from part 1, part A. So our derivative with respect to time of A is going to be equal to the derivative with respect to time of 1/2 of x square root of 625 minus x squared. So dA dt equals product rule. 1/2 times 1 times dx dt times the square root of 625 minus x squared plus 1/2 x times the derivative of the 625 minus x squared is going to be 625 minus x squared to the negative 1/2 times negative 2x dx dt. So our height, dA dt, is going to be the square root of 625 minus x squared over 2 dx dt minus 1/2, and the negative 2 cancels, so that's gone. We have x squared over the square root of 625 minus x squared dx dt. So the last part of this, we're going to plug in 7 for x. We still have our 2 for dx dt. Okay, we end up with 24 plus negative 49 over 24, which is approximately 21.958 square feet per second. That's how that ends. Okay, let's go on to the last example. It says a man 6 feet tall walks at a rate of 5 feet per second away from a light. So here's the light. Here's the man. From a light that's 15 feet above the ground. When he is 10 feet from the base of the light, at what rate is the tip of his shadow moving? And at what rate is the length of his shadow changing? So this distance is y minus x. Our dx dt is 5 feet per second. What we have here is similar triangles. So in that case, lamp on top and the bottom, 15 over 6 equals this distance, which is y, over this distance, so that base of the triangle compared to that base, over y minus x. We can come up with a relationship here. 15 times y minus x equals 6y. 15y minus 15x equals 6y. Subtracting 15y from both sides. Negative 15x equals negative 9y divided by negative 9. Y would be equal to 5/3 of x. So we want dy dt. So taking the derivative with respect to t of y, that's the derivative with respect to t of 5/3 x. So y would be equal to 5/3 times 1 times dx dt. So that's dy dt, I'm sorry. So dy dt is going to be 5/3 times 5 feet per second, which is going to be 25/3 feet per second. So that means that the shadow moving is moving faster than the person's moving. Now for part B, shadow length. Shadow length is y minus x, as we see here. So our d dt of y minus x, it's d dt of y minus d dt of x. That's going to be dy dt minus dx dt. That's 25 thirds feet per second minus 5 feet per second. So that's going to be 25 thirds minus 5 is going to be 10 thirds feet per second. That's the rate at which the shadow is growing. So it's moving because the person's moving, but it's also growing. So if we take away the part where the person's moving, that's our 5 feet per second. 25, that's the total movement, minus because the person's moving. This is the rate at which the shadow is moving. It's just the shadow growing. And that'll do it for Chapter 2. This is the last section of Chapter 2. Hope you guys enjoyed it. Hope this is making sense. I know the word problems can be very stressful. I'm there. A lot of it's drawing a picture, trying to make sense of it, trying to get things to relate. So don't let it stress you too much. Hope you enjoy it. I hope it makes sense. Work the homework. I really encourage people to try things in WebAssign because it'll help you work through problems as well. That's the online component of the homework. So let me know what you think and send me your questions. I'll see you guys online. Thanks.